We'll get started from where we left yesterday. Dhanabal, are you able to hear me?
Yes, ma'am.
We started with what we mean by kinematic analysis. We saw that velocity analysis and acceleration analysis are the important tasks of kinematic analysis. Then we started with displacement uh, or position rather. Position, we saw how to represent the position of a point as position vector in a coordinate system. Now moving on to displacement, there are three types of displacements possible for any body. The first is translation, which is nothing but linear motion, where all the points on the body have the same displacement. So this is a body AB. So this is this point B. After traversing through a path like this, it reaches this point B dash. A moves on to A dash. You can see that this is the path traversed. And when we represent displacement, it is only the initial position and the final position which are to be related. The path taken to reach the final position from the initial position does not matter. So this is translation. As against that, we have rotation, in which different points undergo different displacements. So this is pure rotation. The third is a complex motion, which is a combination of translation and rotation. So this position of AB, the initial position AB, moving on to the final position A dash B double dash, comprises rotation and translation, which is a complex motion. So this complex motion, moving of AB from here to this new position, which is shown in pink, it can be divided into two parts. It can be thought of as translation first, followed by rotation, or it can be thought of as rotation first here about this point A, and then translation. But both of them will be happening simultaneously. For purpose of analysis, we can separate out if required. So we carry out kinematic analysis by two methods, graphical method and analytical method. We will be initially starting with graphical method. So graphical position analysis of mechanism. So the position analysis, when I say graphical position analysis, it is nothing but drawing the configuration to scale. So suppose you need to carry out a kinematic analysis of a 4-bar mechanism. What you have to do is you have to draw the configuration of the 4-bar mechanism to scale, for which you need to know the lengths of all the links, link number 1, 2, 3 and 4, and the initial position of the input link. I mean, rather not initial position, the position of the instantaneous position of the input link. So the link lengths we've already synthesized, so link lengths will be available. And for carrying out a kinematic analysis, you need to know at least for the graphical method, you need to know the instantaneous position of the input link, for which we attempt to carry out the kinematic analysis. So it's nothing but drawing the required configuration to find relative displacement, if required total workspace space occupied the mechanism, and all the other parameters which we saw yesterday. Now let us move on to velocity analysis. Let's get started with some basics of velocity. So the velocity is defined as the rate of change of position or rate of change of displacement. So suppose you consider a body which is initially in position 1. After time interval of delta t, suppose it occupies position 2. displacing through or traversing through a distance, not traversing, displacing through a distance of delta t. Velocity is defined as delta x by delta t. This is with regard to linear motion. Of course, velocity is a vector quantity. So is displacement vector quantity, which means that there is a magnitude and there is a direction associated with the velocity. Okay, a magnitude is there and a direction is there. So here it could be this. Okay, now let's move on to circular motion or angular motion. This is with reference to linear motion. Moving on to angular motion, let us initially consider a planar link. So what you see here is a planar link. Okay, and let it be pinned onto the frame by means of a pin joint, a revolute joint at this location O2. Okay, so this point will not be able to move. And imagine this to be rotating about point O2 with an angular velocity of omega in the counterclockwise direction. Okay, so this body or planar link is said to be having a circular motion or rotational motion with O2 as the center. It is rotating at a velocity of omega radians per second in the counterclockwise direction with O2 as center. Now every point on this body will be subjected to linear velocities, different magnitudes and different directions also. Every point on this will be having a linear velocity except this point to O2, which has zero velocity because it is pinned on to the frame. No displacement, no velocity, no acceleration for this point O2. Now let us consider point A, which is any point, any arbitrary point on the link or on the plate. Okay, let us try to find out what its velocity is. Okay. So let us come to this diagram. Here I've shown the initial position of A. This is O2. This is O2. And I've taken the line connecting A and O2. This is the line connecting A and O2. So that I've drawn separately here. And so O2 I have drawn. I've shown it to be fixed. A is here. This is the initial position of A. After some time, that means after a time interval of delta t, actually the body is rotating counterclockwise. So A would be occupying a new position, which I am calling as A dash. So this is a new position of point A. The distance between point A and O2 and the distance between A dash and O2 will remain the same because it's the same point that we are considering at two different instants of time. Okay. So now we would like to find out the velocity of A, which is the absolute velocity of A. This is called as velocity of A. Now this can also be called as the relative velocity of relative velocity of A with respect to O2. What do I mean by that? If there is a single subscript, it means absolute velocity. Okay. If there are two subscripts, it's called as relative velocity. We'll come to this again later on after I finish this. Okay. So the velocity of A, when I say velocity of A O2, we need to read this as relative velocity of A with respect to O2, with respect to some other point. Here O2 is a fixed point. What is the velocity of O2? Velocity of O2 is 0. So velocity of A in relation to O2 is the same as velocity of A. Again, we'll come back to this once again later on. Now let's try to get an expression for the velocity of A and the direction of the velocity of A. So after over a time interval of delta t, let this line joining A and O2. Let it travel covering an angle of delta theta in delta t instant of interval of time. Okay. Now, what is the distance traveled by the point A? It is this arc distance. The distance traveled by point A during the time interval delta t, it is the arc AA dash. And the velocity of point A will be the distance traveled divided by the time taken. So the distance traveled is the arc distance AA dash and the time taken is delta t. So arc AA dash divided by delta t. So when you have a segment like this, suppose subtending here, okay, subtending an angle of say theta, a radius subtending an angle of theta. Let us consider the segment. If L is the length of the arc, then what is the relationship between L, R and theta? How to get the expression for L, the length, this length in terms of R and theta from your school mathematics? L equal to Manoj.
Yes, ma'am.
What is L equal to? What is this length equal to in terms of R and theta?
Ma'am, d theta by dt, ma'am.
No, have you not studied about the arc length of an arc? Anybody
Yes,
can
ma'am.
answer. Anybody can answer.
R theta, ma'am.
R theta, good. L equal to R theta. The length of the arc, okay, which subtends an angle of theta with a radius of R is given by L equal to R theta, theta in radians. Okay. So here, applying the same concept here, the distance traveled, that is the arc AA dash. What is the arc AA dash in our context equal to? It is the length of the arc. I want to have an expression for the length of the arc AA dash. How much is it? It will be equal to L equal to, apply the concept of L equal to R theta. So L is AA dash. What is R here? Again capital R as going by this, isn't it? Okay, R. Okay, what is, yes, O to A. Good. What is theta equal to?
L theta.
L theta, L theta. So this is the arc length AA dash. And we are trying to find out the expression for velocity. So R del theta in the numerator divided by del t. Okay. In the limit delta t tending to 0, the limit delta t tending to 0, the velocity expression will become R into d theta by dt. So what is theta? Theta is the angular displacement in the rotational motion. So d theta by dt is nothing but the angular velocity which we represent using the symbol omega. So this d theta by dt will be equal to omega and we have an r, so r omega. So what is r omega? Velocity of any point A is any point, arbitrary point on a body which is rotating with O2 as center. So velocity of point A with respect to O2, O2 being the center of rotation, will be given by r omega. So in case of a point on a link which is rotating or on a body which is rotating, the linear velocity will be given by v equal to r omega. So v can be any point. I can find out the velocity of any point p. It could be some point here. Okay. So velocity of point p will be equal to the distance between the point p and the center of rotation, which is O2p. So r will be, what is r? R is the distance of the point of interest. R is the distance of the point of interest. This is the point of interest whose velocity we are trying to find out. From where? From the center of rotation. O2 is the center of rotation. Multiplied by omega of the link on which this point P lies. So like this, you can find out the velocity of any point on the link. You find that the linear velocity of any point on a link which is rotating can be found out as r being the distance between the point of interest and the center of rotation. This is r multiplied by the omega at which the angular velocity at which the link is rotating at any instant of time. Omega could be a constant, omega could be a variable also. And if it is an input link, normally omega will be a constant. For other links, it will be a variable. It will keep on varying with respect to time. Okay. Now on to so if you want to find out the velocity of some other point B, you need to join that point B to O2, and the velocity of B will be given by Vignesh, please call out a name of student.
Harish.
Harish.
432.
Yes, automobile. What is the expression for velocity of B going by this diagram? Harish, please be fast. First of all, Harish, are you there? Is Harish here in our class?
Yes, ma'am, is here now.
Yes. Please be louder, Harish. No, I'm not able to hear. Somebody else?
BO2 omega, ma'am.
BO2 is the distance between the point of interest and the center of rotation multiplied by omega. Good. This is how you calculate the velocity. You can find out the linear velocity of any point. Every point will be subjected to different magnitudes of linear velocity. The magnitude will be in proportion to its distance from the center of rotation. So at the center of rotation, velocity will be 0. As you move away from the center of rotation, velocity will keep increasing. So that's about the magnitude of the linear velocity of any point on a rotating link. Suppose there is a slider moving at a speed of v meters per second. What will be the velocity of a point here? Say A. The whole of the slider will be having the same velocity, is it not? Any point, take any point on the slider, everywhere the velocity will be the same. But then when you have a member or a body or a link which undergoes rotation or combination motion, every point will be subjected to different magnitudes of linear velocity, and the magnitude will be in proportion to the point's distance from the center of rotation. Now moving on to the direction of the velocity. We are talking of infinitesimal intervals of time. Infinitesimal. What do you mean by infinitesimal? Very, very small, tending to 0, not 0, but tending to 0. If it is made 0, then we are not considering any movement at all, and in the limit and in the mathematical terms it will become 0, but we are talking only in the limiting case. So infinitesimal, we are considering an infinitesimal time interval of time delta t, during which the angle traversed through by the link or angle turned through by the link also will be infinitesimal. That means delta t, as delta t tends to 0, delta theta will tend to 0 but not 0. So as you keep on making this smaller and smaller, okay, this is the original velocity vector, velocity of A with respect to O2. This is the velocity of A dash, the same point but at a different instant of time. So as you reduce delta theta, if you take this around like this, in the limiting case, what will be the direction of velocity of A with respect to O2? As I keep on reducing this further and further, okay, A dash will be very near to A, okay, and in that case, where will the velocity vector be? The velocity vector will be at 90 degrees to the radius vector. Okay, so the direction of the velocity vector, the magnitude we saw, it is equal to V equal to R omega. Using this expression, you can find out the velocity of any point. To find out the radius, the direction of the velocity of any point, what you have to do is, suppose I have a point X, the velocity I will calculate as XO2 multiplied by omega. How do I get the direction? I need to join X with O2, and then this will be at 90 degrees. So this will be the instantaneous velocity of X. Of course, this orientation will keep on changing as the body rotates. Had this been rotating clockwise, suppose the link rotates clockwise, then velocity of X would be pointing towards this direction. For counterclockwise direction of omega, this is the direction of velocity of X. So now we know how to find out the linear velocity of a point on a rotating link with respect to the center of rotation. Here the center of rotation is a fixed center of rotation. Now let us consider again a 4-bar mechanism. Like this. Let me name the joints as O2A, B and O4. Okay. Now, if I want to find out the velocity of A here, suppose omega 2 is clockwise, say some 10 radians per second or something like that. So, velocity of A I can find out as what? R omega. What is R? A to O2 is R multiplied by omega 2. This is the velocity of A. I can also write it as velocity of A with respect to O2 because O2 is a fixed. Whenever we talk of velocity of a body, we always take a fixed reference like the ground, the road, or a fixed table, fixed frame, and so on. Okay. So when we talk of absolute velocity of a body or a point, we take the reference as the ground or a fixed frame. Okay. So, but then here O2 also belongs to the fixed frame. So I can write velocity of A as velocity of A with respect to O2 also. It's a relative velocity. We'll come to relative velocity concept now. Okay. So I can write like this. But then when you wish to find out the velocity of point B, moving from velocity of A, okay, moving from A, when you take this link AB, okay, having found out velocity of A like this, now for B, the center of course, we have a center of rotation for B here, which is an absolute, a frame. But then before considering this, let us consider this link AB, okay, third link. So B can be having rotation with respect to A. At this joint A, it is a revolute joint. So if you hold this link, if you hold link number 2 instead of link number 4, link number 1, this can have relative rotation. That is, B can have relative rotation about A. So you can also write the velocity of B in relation to A. If you assume A to be fixed, the velocity of B can be written as you can make use of the same expression R omega. So now R will be B to A, the distance multiplied by omega 3. Okay. So earlier I wrote velocity of A in relation to a point O2, which is a fixed point. But now I am I am relating the velocity of B to another point on the same link. Please see that both points A and B belong to the link number 3. A belongs to link 2 as well as link 3. B belongs to 3 and 4. Okay, and this both A and B belong to 3 also. So you can relate the velocity of any point on link number 3 to A. But I wish to find out the expression for velocity of B in relation to A. So I can write the velocity of B in relation to A as the distance, or same formula, r omega. So BA is a distance r now omega 3, because I am talking about link number 3. Okay. But what is the difference compared to the earlier velocity of A? Velocity of A was written in terms of, or relating to, velocity of O2, which is a fixed point. But when I talk of A and B, when I relate B's velocity to A's velocity, I am relating to the velocity of A, which is not fixed. A itself is moving. So that situation is shown here in this diagram. Okay. So link AB, link number 3, you can think of this as link AB, okay, or link AP. So A itself, this A itself is moving with the velocity of VA, and this point P is moving with the velocity of VP. Okay, so A is moving with the velocity of VA, P is moving with the velocity of P. The orientations, the magnitudes and the directions, let them be like this as shown here, drawn to scale. So now you can write an expression for, see that both A and B belong to the same link. Both of them belong to the same link. So in such a case, you can write the relative velocity of P with respect to A. You can find out the relative velocity of P with respect to A. As an example, let us consider a case. Let us consider a train A and a train B. Initially, both of them, let them be at rest. Both of them have zero absolute velocity. That is, both of them are at rest. So both of them have zero velocity. Since the ground is the railway track is the reference, the absolute velocity is zero. And then talking in relative terms, the velocity of A, considering this case, imagining A and B to be two trains or cars or whatever, velocity of A is zero initially, velocity of B also is zero, let them be at rest initially. Okay, what is the difference in velocity? That also is zero. Now let us consider A to be moving like this, say 5 meters per second. Okay, so now what is the velocity of A? Velocity of A is 5 meters per second. B is at zero velocity, it is at rest. So velocity of A in relation to velocity of B will be, suppose, okay, so 5 minus 0, B considered to be rest. So velocity of A in relation to the velocity of B. So whenever it has to be written like this. When you have two subscripts written, it means the relative velocity of one point or one body with reference to another point. Any relative quantity, always a relative quantity needs a comparison between two items or two elements. Somebody is taller than somebody and so on. So relative, you can say somebody is tall, but then when you need to compare, you need to have at least two persons to compare. Somebody's person A is taller than person B and so on. So like that, any relationship, relative quantity needs to be comparison between two bodies or two items, two persons and so on. Okay. So the relative, you can write the relative velocity. What I mean to say is relative velocity. So relative velocity is nothing but the velocity of one body, the velocity of one body in relation to another body, or the velocity of one point on a link with reference to the velocity of another point on the same link. You can see, please look here. You can talk of velocity difference between two points which are on different links and you can find out the velocity difference between 2 points on the same link. So relative velocity is the velocity difference okay. Relative velocity is nothing but the velocity difference between 2 points or 2 bodies. Okay, and it has to be written with 2 subscripts like this. So you can talk of velocity of A with respect to B. You can talk of velocity of B with respect to A. You can talk of velocity of P with respect to A and so on. Now in mechanisms, in our kinematic analysis, we are more interested in velocity difference between points on the same link, 2 different points on the same link. This is what we will be making use of to large extent. Okay, so now here coming back to this body, point A, it is a single body, it is called as link number 2 here. So A is a point on link 2, P is a point on link 2. So I wish to find out the velocity difference between point P and point A, which is called as a relative velocity. So the relative velocity is, as I told you, the difference in velocity between 2 points. So here velocity of, when I write like this, I need to read it as velocity of P with respect to A. Velocity of A in relation to A. That means if actually A is moving with VA along this direction, P is moving along this direction with the velocity of VP. I would like to find out the difference. Suppose this is say 48 in some units and suppose this is 98 in the same units. I cannot say that the relative difference in velocity is say 50. I cannot say so. Why? Because the velocities are oriented along different directions. Only when the velocities are oriented in the same direction, suppose the velocity of body A is 5 meters per second and the velocity of body B here, suppose it is 2 meters per second. Only since they are oriented along the same direction, I can talk of velocity of A in relation to B as 5 minus 2. Straight algebraic manipulations, addition, subtraction will be possible only when the vectors are directed along the same direction. So velocity of B A with respect to B will be defined as velocity of A minus velocity of B, of course vector addition or vector subtraction here. Since these two are parallel to each other, oriented along the same direction, they can be, the relative velocity can be found out as 5 minus 2, 3 meters per second, which means that velocity A moves along this direction in absolute terms at the rate of 3 meters per second if B is considered fixed. Actually, A is moving. Next instant of time, A would have gone through 5 meters, but B would have gone through 3 meters. So there is a, 2 meters. And there will be a difference of 3 meters every second. Every second, there will be a additional difference of 3 meters per second. That is called as a relative velocity. You can also write or you can also find out the relative velocity of B with respect to A. Okay, which will be defined as the velocity of B if A is assumed to be fixed. The velocity difference between B and A. Earlier we had A and B, now it is B and A. So the velocity difference between B and A will be defined as velocity B minus velocity of A. Okay, it can be thought of as the velocity of B if A is assumed to be fixed. Okay. Now, velocity of B according to my diagram is 2 meters per second. Velocity of A is 5 meters per second. Both of them rightward. Both of them right along the right direction or along the towards the right direction. So, how much will this be? Minus 3 meters per second. What does it mean? What does it mean? What does it mean? It means that actually the difference is 3 meters per second. So for somebody who's sitting on A, he will feel that he is looking at somebody in B. A will feel that it is moving at the rate of 3 meters per second rightward. But suppose somebody is sitting at B, you can imagine yourself to be sitting in a train B, and the train slowly moves. The train in which you are sitting slowly moves. There's another train in the next track which is moving at a faster rate. How will you feel? How will you feel? You will feel that you will feel as if train A is stationary, okay, but then you are moving along this direction at 3 meters per second. Whereas in reality, train A is moving towards right at 5 meters per second. Your train B is moving at the rate of 2 meters per second. But if you look at the next train sitting from here, you will feel as if the other train is stationary and you are moving along this direction at 3 meters per second. So that is what this minus 3 indicates. So if this is positive, this is what we've taken as positive because I had 5 as positive, and then this is a negative direction. So this is the concept of relative velocity. So you must have observed this sitting in train also. Suppose you are seated in a train waiting for it to start, and suppose there is a train in the next track which is moving, you will feel as if you are moving if you look at the train. Only when you look on the side, the platform and all that, train, trees and so on, you will feel that you'll come to know that you are stationary, the other train is moving. Is it not? So this is the concept of relative velocity. Okay, so now coming back to our problem or link. So I would like to find out the velocity difference between point P and point A which belong to the same link, which is called as a relative velocity. So the point here is that point A also it's moving. That is the point. Okay. So velocity of P with respect to A is nothing but the difference in velocity between point P and point A, which you have to write as Vp minus Va. Please mind that they are all vectorial. Algebraic subtraction is not possible. Like 98 minus 48 is not possible because they are all oriented along different directions. So this is the relative velocity. So if you are given with the velocity of a point on a link, if you know the velocity of a point A on a link, and if you know the relative velocity of some other point on the link in relation to the earlier point, the first point, you can find out the absolute velocity of point P. So I've just rearranged this equation to get at this. Vp equal to, I've just taken this to the side. So Vp equal to Va plus Vpa. So what we mean to say is, I can find out the velocity of any point P on a link if I know the velocity of some other point on the same link plus the relative velocity of that point with reference to this point. For the case of bodies which are rotating, say for example, link number 3 here. Okay, considering link number 3, if I wish to find out the velocity of B, I can write an expression for the velocity of B if the velocity of A is known. The velocity of A will be initially known because we know the link length AO2. I told you that all the link lengths should be known to carry out a velocity analysis. So AO2 will be known. I need to know the input velocity also. So velocity of A will be available. Please note that velocity of A is not 0. Okay. Then I told you can find out the velocity of B with respect to A. Please note that both A and B belong to the same link. And at this joint, it is a relative rotation. So if you imagine A to be held, try to hold that pin at A. I mean, not the pin. You try to hold the link at A and try to move this link. It will be a relative rotation. For all the points on members which have relative rotation, velocity, linear velocity can be found out making use of this expression as we saw in the blue color planar link. So here also you cannot write velocity of B as velocity of B equal to BA. For AB, for the link AB, where will be the center of rotation? This will be the center of rotation. You should imagine this to be fixed. Then you should imagine this to be moved. You find out what type of motion is possible. It's a relative rotation now. So for members which undergo relative rotation as well as for members which undergo complex motion, I told you this can be made use of. Okay, so velocity of B can be written as velocity of B with respect to A multiplied by omega 3. Yes or no? Please somebody answer. Shankar? Is there a Shankar in class? Yes, Shankar.
Yes, ma'am.
Can I write like this? Is this correct to write like this? I wrote velocity of A as AO2 multiplied by omega 2 because A belongs to a link in which O2 is there, which is a fixed point. O2 does not have a displacement, velocity, acceleration. It doesn't have any of them. Okay?
Yes, ma'am.
Now, can I make use of the same concept of V equal to R omega for B to finding out the absolute velocity of B?
Yeah, ma'am. It also fixed, ma'am.
Okay, Vikram,
Yes, ma'am.
can I do like this? Is this correct? Is it correct to write like this? Not yet clear? Not
Yes.
sure?
Not sure.
Not sure. Okay. See, the velocity of a point A, say for example, this link number 2, you can write the velocity of a point on link number 2, any point for that matter, not necessarily link A. You can write the velocity as the distance between that point and the center of rotation, that is R, multiplied by the omega of that particular link on which A lies. Is this clear? When I write like this, okay, the center of rotation, you need to find out the center of rotation for this point A, that is this point. This is correct only if this is a fixed point. Now O2, it's a fixed point. Whenever you show a pivot like this, what does this mean? This is ready to form a joint between the fixed link and some other link number 2 here. So this particular point, which I've called as O2 here, it belongs to the frame 1, it belongs to O. It is a common point. O2 is a common point for link number 2 and link number 1. Since it belongs to link number 1 does not have any motion, no displacement, no velocity, no acceleration. So O2 is a fixed point. And for any point on link number 2, say for example S, you can write the velocity of S as R omega, where R is the distance of point S from the center of rotation multiplied by omega of the link on which that S lies. Okay, you can write the absolute velocity of a point on a rotating link like this only when this point is a fixed point. Is it clear?
Yes, ma'am.
Okay, now we are talking of course you can, for A also I can write like this. For point A also I can write like this, AO2 multiplied by omega 2 is correct. It's the absolute velocity of A. But for a point B, imagine a point B here. Okay, again between A and B, between link number 2 and link number 3, there is a relative rotation. It is the relative motion between link 2 and B about point A is a relative rotation. So wherever you have a relative rotation, this V equal to R omega holds good. Okay, but whether it is this v equal to r omega, whether it is absolute velocity or whether it's a relative velocity is dependent on whether you are considering with respect to a fixed point here or you are considering the velocity of b with reference to a moving point. Okay. Now this velocity of this point B can have relative rotation about point A. But point A itself is moving. Point A itself is moving. Right? So velocity of B has to be written as velocity of B can be written as velocity of B can be written as velocity of A plus velocity of B with respect to A, like what you have here. Okay. In other words, let me clear up some missing. Okay. So now here I have 2 points, both of them A and P in this link, both belonging to the same link. Okay, and the velocity of A is like this, velocity of P is like this. I can find out the difference in velocity between P and A, which is called as the relative velocity of P with respect to A as difference. I've already told that it is difference in velocity. So obviously Vp minus Va. So this is the expression for relative velocity, where Vp is absolute velocity of point P, Va is absolute velocity of point A, Vpa is the relative velocity of P with respect to A. If you wish to write it as relative velocity of A with respect to P, then you just have to interchange the locations of Vp and Va in this expression. Now rewriting this expression, relative velocity expression, bringing Vp to keeping Vp on one side, the other two on the other side. So the velocity of any point. So this expression, what does it say? The velocity of any point. When I have one subscript, it means the absolute velocity. When I have two subscripts, it means the relative velocity. So the absolute velocity of a point P on a link, on any link, can be related to the absolute velocity of some other point on the same link. For example, here, both of them belong to the same link, plus the relative velocity of between the two points on the same link, VPA. The same way, so why do I have to go for this expression? Why not? Why not use this expression? This expression can be written as absolute velocity only when the reference is a fixed point. So for A, when I write V equal to R omega, I am referring to O2, which is a fixed point. If I write the expression, velocity expression for B as velocity of B equal to R omega, I need to make use of A as a reference, but A itself is having some velocity. Okay, so the velocity of B, now considering link number 3, I have 2 points A and B on link number 3. A's velocity is already available like this. A's absolute velocity itself is available because this O2 reference is a fixed point. Now, the velocity of B we are relating to A, which itself is moving with some velocity. So, velocity of point B, which lies on link 3, will be related to velocity of A plus the relative velocity of B with respect to A. That means, what is where B with respect to A? It means the velocity of B if A is fixed, if A is considered or assumed to be fixed. That is this. But A is not fixed. A itself is having a motion or velocity. So that needs to be added here, of course. all of them vector addition. Okay. So now B with respect to A. Okay. So this motion of B with respect to A. When I say with respect to, you should imagine that second with respect to what? With respect to A, you should imagine A to be held. You should imagine A to be not moving. Okay, if you try to hold A, what type of motion will be have? It is a relative rotation. So this is the velocity of B if A is imagined to be held fixed. So this can be written as V equal to R omega, where R is AB or BA. A is the center of rotation. A is the center of rotation for BA multiplied by omega 3. But A itself is not fixed, it itself is having a velocity, so that needs to be added like here. Okay. So that's how you find out, you can relate the velocity of a point on a link to the velocity of some other point on the same link. I assume that it's clear. So as I told you, velocity of V equal to R omega, this expression can be made use of as absolute velocity if the reference point is a fixed reference point, like relating A to A and O2. When you relate A and O2, making use of V equal to R omega, O2 is a fixed point, in which case I get the absolute velocity of A. When you relate B to A, making use of the same expression R omega, it is a relative velocity because A itself is moving. A is not fixed. So here, this is a link. This is a single link, link number 2. I imagine it to be fixed at this point O2. Okay. And it's a ternary type of link, or at least the link is of a triangular shape. Right? How will you find out the velocity of A? Velocity of A can be written as velocity of A with respect to O2. Both of them. In this case, the relative velocity and the absolute velocity are the same. When I say absolute velocity, I mean the velocity with reference to a fixed frame. Here, if I find out the relative velocity involves 2 points or 2 bodies. Absolute velocity also involves 2 points or 2 bodies. The only thing is that the reference is a fixed frame. Reference is a fixed frame or fixed, doesn't have any movement. Okay. Relative velocity is written between body 1 and body 2 or points 1 and point 2. And in case the second body is a fixed point or fixed body, then the relative velocity is the same as the absolute velocity. Okay. So VA is the absolute velocity of point A here. It can also be treated as the relative velocity of A with reference to O2 because O2 is a fixed point. It can be written as R omega, where R is AO2 multiplied by omega 2. Similarly, velocity of B can be written as, because all of them, please note that all of them belong to the same link. A, B, O2, all of them belong to the same link, namely link number 2. So velocity of B can be written as, the absolute velocity of B can be written as the relative velocity of B with respect to O2. Please see that O2 is a fixed point and it can be written as R making use of R omega. R is BO2 multiplied by omega 2. So in case you refer the velocity of a point to another point which is fixed, in such a case, the absolute velocity and the relative velocity are the same. This is okay. Now, if I would like to find out the velocity of B in relation to A, if I wish to write the expression velocity of B with respect to A, is it equal to BB? Yes or no? Velocity of B with respect to, I wrote here velocity of B with respect to O2 is the same as velocity of B. Now, velocity of B with respect to A, is it also equal to B, velocity of B? No? Why?
Ma'am, cause A is moving, ma'am.
Good, very good. What's your name?
Krishant.
Kishanta?
Ma'am,
Kishant?
20M 432, ma'am.
Krishant.
Krishant.
Trishant.
Yes, ma'am.
Okay, good, very good. Very good. So now this is relative velocity of a point B on a link 2 with respect to another point A on the same link, which itself is moving. A itself is moving. Please note the difference between velocity of B with respect to O2 and velocity of B with respect to A. Whenever you have two subscripts, it means relative velocity. So this is the VBA is the velocity of B if A were fixed. If A were fixed. Velocity of this B O2 is the velocity of B if O2 were fixed. But O2 is really fixed. If O2 is really fixed, then it becomes the absolute velocity also. Whereas velocity of B with respect to A, B is a point on link 2, A also is a point on link 2. It's a relative velocity of B with respect to A, but A itself is moving. Okay, so you cannot, this is not an absolute velocity, it is not equal to BB. In other words, let me explain a little further. What is the definition for relative velocity? It is the velocity difference between the 2 points which are involved. Here 2 points are B and O2. So velocity of B minus velocity of O2. What is velocity of O2? Shank.
What is fixed, ma'am?
What is the velocity?
0. In a fixed.
0. So that's how it becomes VB. VBO2 becomes equal to VB. Whereas when you write the relative velocity of B with respect to A, it is now by definition it is VB minus
VA.
VA. And what is VA? What is VA? VA we've written here. First of all,
CO2 omega.
omega 2. First of all, it is not 0. It is not 0. That much is clear.
Yes, ma'am.
That much is clear. So VBA is VB minus VA only. It cannot be written as VB. Why VBO2 is VB and why VBA is not VB? Is it clear now? Going by the equations?
Yes, ma'am.
Yes. Okay. So this is how you need to find out the velocities. So velocity of B, of course, we know. Velocity of B, we know magnitude and direction. How is the direction? The direction will be you have to get velocity, the direction of velocity of A. You need to join A with O2 and then draw a perpendicular. So this is the direction of velocity of A. Similarly, to get the direction of velocity of B, you need to join BO2 and perpendicular to that BO2. This is BO2. Join, okay, and draw a perpendicular to BO2. This will be the direction of BB. How to get, so please mind that they're all vectorial. They are oriented along different directions. So suppose I find that VB is some quantity and BA is some quantity. I cannot make algebraic calculations like this. It is not correct. They have to be drawn to scale. You can adopt graphical means or you can adopt analytical means. So vectorial subtraction or addition needs to be done. So if I give you this diagram, how will you find out? How will you find out the velocity of B with respect to A vectorially? How to write velocity of B with respect to velocity of B minus velocity of A? Velocity of A. If it is to be drawn vectorially, then what do you have to do? You have to start with an origin to represent zero velocity. So you can draw what is called as vector polygon to find out the velocities. So to find out velocity of B with respect to A in magnitude and direction, you can go for graphical method. You can start with a point which is called as a pole, which signifies 0. If it's velocity polygon, it signifies zero velocity pole, zero velocity. At this point, you have to mark all the points which have zero velocity in your diagram. Can somebody tell me in the diagram that is shown here, is there any point which has zero velocity? Please be fast.
O2, ma'am.
O2, good, very good, O2. So O2 has zero velocity. Then this is VA. This is VA. We need to draw VA to scale. Suppose VA is 46 and VB is 96. You need to draw a length equal to 46 millimeters or whatever. Okay. This represents velocity of A to scale. To scale means orientation also should be maintained. You have to draw them parallel. And then what is this VB? VB is say 96 units and it is directed like this. So it's absolute velocity. So the pole point becomes the absolute reference. Pole point has zero velocity. So for all your polygons, the pole point becomes the absolute reference. That is, the pole signifies a fixed frame. So to get VB, you have to draw to scale VB like this. This is velocity of B. Magnitude is 96. For my example, direction is like this. Okay. Then the third, this one, the third side of the polygon, this is called as velocity polygon. This third side, this gives you the velocity of B with respect to A. This gives you, the third side gives you velocity of B with respect to A. Let us try to write expressions for this. Okay. VA, shall we apply the concept of vector addition? VA, please look at the diagram. This is polygon. Look at the velocity polygon, velocity diagram. VA, please give me an expression for the vector addition. VA plus going in the same, the arrow marks going in the vectors going the same direction like this can be added. VA plus VBA will be equal to VB. VA plus VB equal to VA plus VBA equal to VB. This plus this is equal to this. Looking here, you can rewrite this as VB equal to VA plus VBA. Isn't it? That you can see here in your diagram. So when you have a polygon like this, keep on, suppose you have vectors to be plotted like this, many vectors to be plotted, say vector 1, vector 2, vector 3, vector 4. Okay. Suppose this is the origin of the vector diagram. Suppose what will be the addition of these vectors equal to? What is v1 plus v2 plus v3 plus v4 equal to? Equal to?
0.
Equal to?
OD.
OD taken in the opposite direction. The vector sum of all these vectors v1, v2, v3 and v4 will be equal to the closing side of the vector polygon, the closing side of the polygon taken in the opposite direction. When I say closing, it is this vector. Please try to understand. This will be the closing vector. Taken in the opposite direction is this. This is the resultant. So resultant of many vectors, how many ever you have, they can be drawn as adjacent sides of a polygon. You can have as many as you have. The resultant will be equal to, graphically, if you represent them graphically, the resultant will be equal to the closing side taken in the opposite direction. And that is what we are doing here. We have only two vectors to be added. Okay. This is vector A, velocity of A. This is true for any vector, velocity, force vector and so on. This is velocity of B with respect to A. So velocity of A plus velocity of B with respect to A will be velocity of B taken in the opposite direction. So with this vector manipulation, graphical method, we will be making use of velocity polygons, the graphical method, to carry out velocity analysis. Velocity analysis of mechanisms, simple mechanisms, through the graphical method. This method is called as a relative velocity method. There are other methods as well, but we will be solving through the relative velocity method initially. For the timing, for a moment, let me just go out. I'll just touch upon this. It's again review only. So need for velocity analysis we found out, we learned earlier yesterday. It's a step towards acceleration analysis. So what are all the, so now we are entering into velocity analysis of a mechanism. We'll be starting with 4-bar mechanism. So the inputs required, what should you know prior to starting with the kinematic or rather velocity analysis? You should know the dimensions of all links. I assume that synthesis is over for a mechanisms design problem. So dimensions will all be available. And then the configuration, of course, I'll come to that. And then you also should know the velocity of the input link. Usually the crank will be the input link, driving link. So you should know the angular velocity of the driving link if it's a if the driver is a crank. The outcome, as I told you, will be angular velocity of all the links which undergo rotational motion and combination motion, and linear velocity of any point of interest in your mechanism. So we will be drawing what is called as a velocity polygon, which is a vector polygon whose sides will represent the velocities of various points on the links of the mechanism, and it contains information about the magnitudes and directions of velocities of various points. Okay. Quickly, let me try to explain the velocity analysis of a 4-bar mechanism. Anyway, I think I'll have to repeat it tomorrow. Just for the time being, I will give some introductory remarks about this before closing. So let us start with velocity analysis of a 4-bar mechanism. We go by the graphical method. It is the relative velocity method. Relative velocity method. Under that graphical method, you can also have a vector analytical method that we are not doing it today or immediately. So relative velocity method, the graphical technique is what we are going to do, in which we will be drawing the velocity polygon to complete the velocity analysis. The first step is to draw the configuration diagram to scale. Configuration, some books also refer to it as space diagram to scale. Okay, what I mean to say is you need to draw the mechanism to scale by adopting the linked lengths. Suppose I say L1 is 80 millimeters, L2 is 25 millimeters, L3 is say 45 millimeters, and L4 is say 55 millimeters. Will this qualify as a Grashofian mechanism? Please somebody tell. Will this be a Grashofian mechanism? Yes or no? What is the condition for Grashofian mechanism? Shortest plus longest. Less than the sum of the other two. Is it so?
Intermediate lengths. Yes, ma'am.
Is it a Grashofian mechanism? Amava?
No, ma'am.
No. Okay, then I think I will change. Okay, even if it is not, it doesn't matter for carrying out a velocity analysis. So let us retain like this. So the link length should be known, and I also should know the angle corresponding to link number 2, for which I need to carry out a velocity analysis. Please mind that for different values of theta 2, the results will be different. Okay, so first draw the configuration to scale by making use of all these link lengths and the given angle. Suppose this angle is 60 degrees. So how will you do the configuration diagram? You have to start with the point to represent O2, and then L1. L1, how much is it? 80. You have to draw another point here which represents O4. This should be O2, O4 should be 80 millimeters, and then I need to draw a line at what angle? 60 degrees, and mark on it a length equal to L2, which is 25. May not be there, maybe a little closer to O2. Okay, so this will be marked as A. Then what do we do? So shortest and longest have been, let's assume this is the frame ground. Okay, and then how to get at B? With L3 as radius, from A cut off an arc 45 millimeters, with A center cut off an arc, and then with 55 millimeters O4 as radius cut off the previously drawn arc, and then mark a joint out there and then connect them. So that point will be B, connect them. So this is how you draw the configuration diagram. So first of all, draw O2 and O4 to scale 80 millimeters. Then mark 60 degrees, an angle, a line at 60 degrees, and on it cut off a length equal to 25, that is L2, to get A. With A as center and L3 as radius, draw an arc. With O4 as center and L4 as radius, cut off the previously drawn arc. So this length will be, how much will it be? It will be 45. This will be 55. This is how you get the configuration diagram. This is called as the configuration diagram. Okay. Now we need to draw the velocity polygon. The actual drawing of velocity polygon, I think we will defer to tomorrow. Now I wish to say that you will be getting a velocity polygon. This velocity polygon, even though the mechanism is the same, for different values of theta, even if you change theta by 1 degree, 61, 59 and so on, the velocity polygon will be different. The answers will be different. So apart from the link lengths, you should also be knowing the magnitude of omega 2. Magnitude and direction of omega 2. Let's assume that to be 10 radians per second clockwise. Our aim will be to find out omega 3 and omega 4. Our aim will be to find out omega 3 and omega 4. You can also find out the linear velocity of any point of interest. Can take any point on this link or any other link. Say for example, I can also find out the velocity of a point, say x here, or if you wish, if you have this link to be of a different shape like this, suppose link 3 is a planar link with a triangular shape like this. This is link 3, single link. This is okay. I can find out the velocity of any point if here or anywhere on this. So velocity of point, say x, or velocity of point, say for example g, velocity of f, whatever velocity you want, velocity of whatever point you want, you can find out. So please mind that for links it is omegas, and for points on various links it is velocities. Okay. So with this example, we will try to draw the velocity diagram tomorrow. With that, I would like to stop. Thank you all. Thank you.